variance compared to this stratified sampling estimator, right? Of course, this is the estimation of a single copy, single replication. If you have a simulation budget of n, then it's 24 over n and 8 over n. So you see significant variance reduction. Example 2. Approximation of integrals. The objective here is to use Monte Carlo simulation to estimate this integral without specifying what h is, right? Okay. So we have an h function which we wish to integrate from 0 to 1. We call that theta. It's easy to see that this thing it can be interpreted as the expectation of an h of a u where u is uniform 0 to 1. Right? We have seen this many cases, many examples, right? Okay. So once we see an expectation, we're happy because we know that we can keep generating the copies of u, and we apply HU and we average, right? Okay. But that's crude Monte Carlo. So right now, let's stratify on discrete random variable s. Let's just say s equals I if the u falls into a successive interval. So u falls into this interval, this ith interval, s equals I. Right? We're creating some auxiliary discrete random variable s. Okay? So we apply this desired value, this conditional expectation formula. We know that theta is equal to the conditional expectation given s equals I times the probability s equals I, but s equals I with the probability u falls into this interval, which is measured by its length. So the probability s equals I is just 1 over k, according to how it's defined. Okay, no problem. Alright, given that s equals I, or given that u falls into this ith interval, okay, u given s equals I will be uniformly distributed in the interval, right? So basically s equals I means u falls in here. Given that u falls in here, the distribution of u will be uniform in that interval. Easy, right? Okay. To verify, how do we verify, right? I mean, here this formula aims at showing this statement, right? Why this holds. To verify, let's compute the CCDF and the CDF of u given s equals I. All you need to apply here is Bayes' rule. So PA given B is equal to PAB divided by PB, and this condition says u is less than small u, and this condition says u is between these two intervals, right? And this small u is picked within the interval, so these two conditions are combined into a subset, right? So u, I think I'm missing something. And this is a typo here. It should be big U greater than this, less than that. Because this is saying what? This is saying big U is less than small u. This is saying big U is greater than this, less than this. So combining the two conditions, it should be big U greater than the lower bound, less than this upper bound, minimum with this upper bound. So this probability should be this guy, smaller than big U, smaller than this thing, right? Okay, type of it. Which has probability this, right? So, okay. And here the denominator here is just the probability of this, which is 1 over k, right? So it's 1 over k, so it's k times, right? So again, this is a typo. It should be this guy less than big U, less than upper bound. So I'm missing something in the middle. Okay?
I think it's not missing. The right one is minimum of k, I over k and mu.
No, but no.
It means the minimum is u or I over k.
No, but I have a probability here. I need to have a random variable in somewhere, right? I'm missing my u. I mean my big U. Right? My big U is missing. So what I'm saying is, it should be this guy less than big U, less than this upper bound. Right? So you can easily compute that this probability, the correct version of it, of course, is going to be the difference between this quantity and this quantity. So I mean, you can easily show that this is equal to this, and that is exactly the CCDF of a uniform random variable within this interval. Because it's one when you're beyond this point, or it's 0 when you're the other side, and it's a linear function within the interval, right? It's easy, right? So anyway, what I'm trying to show, I'm trying to use mathematics to verify this statement, right? So given u falls into this interval, the distribution of u should be uniform within the interval, okay? Which is pretty obvious. Okay. All right. So the conditional probability density function. So here we have this distribution function. So we have this CDF, right? Take a derivative, we should have a conditional distribution function, which is k. Indicator small u falls into this interval. Why is it k? Because the domain is very, the length of interval is very small, though. You have to make sure that the area covered by this curve is 1, right? So it's going to be k. So it's k, right? So it's uniform. So k times the length of this interval, which is 1 over k, gives you 1. Okay. So how to apply the stratified sampling estimator? Stratified sampling estimator. If you decide that you're going to stratify over this S, then you should be able to estimate expectation of HU given S equals I. Right? You know the probability of this is 1 over k. So you can generate, n prime many copies of this H of U given S equals I. Right? This is the allocation of the overall budget to the ith case. Right? So basically I generated U1 super I to U n prime super I that are conditional distributed. The H of U, right? So these are the conditional uniform random variable. Now given that happens, this H of U, the expectation of HU is estimated by the sample mean, right? So basically what I'm trying to say is that this is the estimator for this conditional expectation, because each U is no longer uniform 0, 1, it's the uniform I minus 1 over k to I over k. Got this one, right? Then my stratified sampling estimator is equal to, applying this conditional expectation is equal to this guy, right? Because each p is equal to 1 over k. Question about this? Okay, here. So the pi here is the 1 over k, right? I chose the same pi, so I'm allocating the same ni to each case. What if I pick k to be very large? So k is what? K is the number of cases that you have, right? So number of cases, right? So pi, p1, p2, pk. Usually you should leave enough sample n prime for each case. So k cannot be too large. What if I set k to be equal to n, so I have only one sample for each case? So I have many cases, many intervals, but I only have one sample here for each case. Okay? Now stratified sampling estimator and the raw Monte Carlo estimator are the following. So this estimator here becomes this guy. Why? Because 1 over k is 1 over n, right? So k is equal to n. And this bar, this x bar is just one sample, because n prime is 1. Right? So here k equals n, n prime equals 1, then this x bar is just one sample, because n prime is 1, so it's one of them. One of them, right? And this 1 over k is 1 over n. So, okay, look at the crude Monte Carlo estimator, which is just the x bar of n equals 1 over n summation of id copies of h of ui. Each ui is uniform 0, 1, right? I have the same formula, except that my u's are not id, because each ui represents each case. Each ui is a conditional distribution of uniform within each interval, right? So each ui is uniform distribution in a small interval. In other words, how do I simulate my ui? I do stretching, I do shifting. I simulate the ui that is uniform 0, 1, and I stretch and scale. Okay. So there's a fundamental difference between this guy and this guy, although the formula looks very similar. this one should achieve a variance reduction. Here's the intuition. We make sure UIs are more regularly uniformly distributed across all 0-1 interval. If you do this, if n is not large enough, you can't make sure that UI covers the entire 0-1 interval. It's possible UI are in the middle, UI are towards the left or towards the right. But if you do what I did here, your UI is already distributed within each interval, because you have randomness, because you don't know where is UI in itself in its own interval, but at least you know that you have one copy of UI within each interval, right? It's more regularly uniformly distributed. Make sense? In that way, you reduce variability, right? I can further improve. Okay, this is the idea, right? So what have we done here? The objective here is to use Monte Carlo simulation to estimate this integral, right, for an h function. We have this stratified sampling estimator. Recall that previous problem approximating pi, right? We have this function h of u in the form of its square root 1 minus u squared. Remember this? This is an exercise in method 3. The expectation of some h function 1 minus u. So this goes back to conditional expectation. Problem 2. Right here. No. Here, right? So this is page 35. Example 1, estimation of pi. So the goal is to estimate pi or pi over 4, and we apply the conditioning estimator. We have a function, we're estimating in the square root of 1 minus u squared. Remember this? Okay. Come back. Let's see if we can use stratified sampling to further improve that estimator there. Okay. See, this is some h function of u, right? So estimating pi using I, the uniform, the crude Monte Carlo estimator would be this. I mean, the 4 comes from the 4 pi over 4, right? So multiply by 4, you have pi. Right? I'm multiplying 4 on both sides, right? If you do stratified sampling, you're not going to do this. You're not going to do a uniform I, the copies of uniform between 0 and 1. You're going to do independent uniforms, but not identically distributed. Each uniform will be uniformly distributed within its own interval, right? Think about this case, right? Here. The uniforms with the superscript I are not ID. They're independent, but they have their own domain, right? Their domain do not overlap. So this is the new estimator. This will help improve. This will achieve a variance reduction. Further improvement can be achieved using antithetic variables, right? This is one estimator, and why don't I just, average this guy with its complement. By complement, I mean replacing UI by 1 minus UI, right? If I replace UI by 1 minus UI, I cancel out with the 1, I have I minus UI. So I have this guy plus the 1 minus u version of it, and I divide by 2, so I have a 2 over n here. So I can further improve this estimator by applying the idea of antithetic variables. Right? Make sense? So when you have multi-method, right, sometimes you can combine and apply more than one method to achieve additional variance reduction. Example 3. Consider a loss of insurance company. Okay. Suppose L is equal to summation of Vj and n is geometric. Let's say the total. So this is so putting this in the context of a insurance company, and n is the total number of claims, car accident, which is geometrically distributed with probability p, and the Vj is the size of the j's claim. So we assume I, the structure of j, and we assume some distribution for j. Let's say, vj follow this distribution. Not important, right? Basically, you are able to do inverse transform to generate a copy of it. Objective, for a large L, let's say L is equal to 1,000,000, estimate the probability of a large loss, which is a rare event. What is the probability that L is greater than a large number here? Rare event, right? The crude Monte Carlo estimator, you're going to generate Ni, the copies of an indicator, and the indicator equals 1 if this summation is greater than L and 0 otherwise. And you average this indicator, right? Take the sample mean. This is the crude Monte Carlo estimator, right? So in each run, generate the N using our geometric random variable algorithm, which can be done by using one uniform, right? Depending on what value you see from step 1, generate Ni, the copies of V, and sum up. Return a 1 if the sum is greater than L, otherwise you return 0. Okay? Crude Monte Carlo. What can we do here to improve? How do we make use of the idea of stratified sampling? If we do, what do we stratify on? What kind of random variable do we treat as a stratification variable, right? The issue is we can choose to stratify on N, because N is something strongly related to L. So if you happen to have many claims, it's more likely for L to be greater than this large number, right? The issue is, there's one issue here. You have infinite possibility of N. N is geometric random variable, the domain of N is unbounded. If you have a K which is infinity, you have infinite many cases, how do you allocate your simulation budget? You are allocating your simulation budget N to K cases. But K is infinity now. Okay? So you have to truncate, right? Pick a Y, which is your stratified sampling estimator.